Hi everyone. I just wanted to post a short video here in which I'll walk through a simple example of solving a decision tree problem. So I'm on page 237 of chapter 10 of the course packet, and what you see here is a simple example of a decision tree. This is for the problem where our decision that we face is whether to build a wall or not to protect a house in the event of a mudslide. So here, if you think about the four main steps that we list in the course packet for solving a decision tree problem, this is step one right here. Put the temporal order of events as they unfold in time in the tree from left to right. So in this example, our first decision that we face is whether to build the wall or not. And then after we build the wall, the mudslide will either happen or not. And assuming that we've built the wall, if the mudslide happens, then the wall will either hold or not. All right, so I'm going to walk through just a couple of examples of how we apply the main rules here, which I've listed in the course packet, which are 2 and 3 here. For every stochastic node or random node, compute the expected utility at that node. And in this particular case, our utility will be measured in dollars, although in general it doesn't have to be. And then 3, for every decision node, pick the course of action with the highest expected utility. And so the diagram on page 238 has a little bit sort of more zoomed in example with some of these expected values filled in. So let's first start from right to left. So when we solve a decision tree problem, we work backwards in time. And the logic here is that the events that happen later, their expected values influence our decisions that happen earlier. Okay, so let's first start with the terminal nodes of the tree. So the things that we've got dollar values here next to these arrows. And so what do these numbers represent? Minus 40,000, minus 1,040,000, and so forth. These numbers represent the net payout, or in some cases maybe a net profit. In this case, it'll be a net cost to us of having traversed a particular sequence of arrows on the tree. So let's take this as an example, this node right here. So how did we get this $1,040,000 figure? Well, we traversed this arrow, and then this arrow, and then this arrow. And every time we traverse an arrow, there's some potential gain or loss associated with following that path. So here, if we decide to build a wall, that costs $40,000. So along this arrow right here, we incur a $40,000 cost. So now let's say we traverse this arrow right here. So if there's a mudslide, well, there's no cost quite yet along this arrow because the cost will ultimately be realized depending on whether the wall holds or not. So in our accounting, that's negative 40,000 and that's 0. Now let's say we go along this arrow, the wall doesn't hold. Well, in that event, which happens with 5% probability, there's a $1 million cost incurred, which is the value that we would have to replace of the house. So we get this minus $1,040,000 figure by just adding up the gains and losses along every arrow in the path. So here, minus 40,000, 0, minus a million. All right, let's work that out for this one up here. So in that case, minus 40,000 if we build the wall. If the mudslide happens, 0, and the wall holds, there's no cost whatsoever. So summing up the gains and losses along those arrows, we get at the minus $40,000 figure. And of course, we're applying a similar recipe to these other terminal nodes of the tree. So for this one down here, if you don't build a wall, no cost, and no mudslide occurs, no cost, and so the net gain or loss is 0. All right, so that now gives us the expected value. In this case, we're thinking of value and utility as being the same thing, of all of the terminal nodes of the tree. Now let's work right to left, so let's start up here. Let's try to calculate the expected value of node D. This is a stochastic node. And so this is going to be a simple expected value calculation. There's a random variable here. If we get this option for the random variable, we incur a minus $40,000 cost. If we get this option, we incur a minus $1,040,000 cost. Those events happen with probability 95% and 5% respectively. So if you simply calculate the expected value of that probability distribution, where these are the events and these are the corresponding probabilities, you find that the expected value of node D right here is minus $90,000. Okay, so now we're working right to left here. So what about this minus $40,000? So now we're in node B, working backwards to our left. So here in node D, there's an expected value of minus $90,000, and here at this terminal node, there's an expected value of minus $40,000. So now working backwards, we're sitting at node B. and we ask what's the expected value of node B. So let's imagine there's two possibilities for this random variable. Either we traverse this arrow or we traverse this arrow. If we go up here, well, we've reduced node D to an expected value of minus $90,000. So that's just like incurring a $90,000 cost here. Similarly, if we traverse this arrow, if the random variable comes up no, we incur a minus $40,000 cost. So if you calculate the expected value, 1% minus 90,000 and 99% minus 40,000, you get the expected value of node B, and that's minus $40,500. Great, so now we've solved the entire branch of the tree all the way up to the decision node, node B. Let's move to the bottom half of the tree. So again, we've calculated using the simple recipe of adding up the gains and losses along the arrows as you traverse the path, the final values of these terminal nodes right here. And now let's calculate the expected value of node C. So with probability 99% you incur no cost, and with probability 1% you incur $1 million cost. That's what happens if there's a mudslide and you haven't built the wall. So the expected value of that probability distribution is minus $10,000. And now we're basically done because we've got node B up here with an expected value of minus 40,500, node C with an expected value of minus 10,000. And so the principle of expected value would say at this decision node, take the option with the highest expected value, and that's this node down here. Now that may not sit well with you if you have a risk-averse utility function. You may not want to reduce the problem to an expected value, and if that were the case, you would want to recalculate all of these expected values applying a utility function to these terminal outcomes right here. In this case, we're just treating value and utility as if they're synonymous, and so the way we've solved this is ultimately at node A1 here, we take this path because it has the higher expected value. All right, so to summarize the basic steps of solving this decision tree, you start from right to left, and to get the very rightmost nodes, you just add up the gains and losses along the arrows as you get there along the path. We reduce every stochastic or random node to an expected value, or more generally an expected utility, and we apply that recursively right to left. So here, having reduced D to an expected value, we can now calculate the expected value of B. And that now allows us to apply Rule 3 at the decision nodes, take the option with the highest expected value. So it's the same steps in any complicated decision tree problem. This is an especially simple example. The decision tree you've got on your homework problem is a little bit more complicated, but that same basic recipe will allow you to solve the problem.